So far, all of our controllers have been some variant of PID controllers. In this video, we're going to introduce the idea of a few new types of generalized controllers, and then really just motivate the concept that we can now think about our controller as a generic transfer function, and we're going to select it in order to shape the closed loop behavior, essentially what you want it to do to the process plant. And this is also the reason why it's called a compensator. A controller is oftentimes a compensator because we think about it as compensating some of the problems or some of the issues that the natural plant brings with it. We started thinking about kind of generalized transfer functions as our controllers when we represented our PD controllers as a gain multiplying some zero, where this z, we introduced this z as really being the ratio between the derivative or the proportional and the derivative gains for a PD controller. But you can see we already moved to this idea that we can think about positioning the gain, picking this gain k, and also choosing where this zero is located. And so now we're going to extend this idea to controllers or compensators that include both poles and zeros. And so the first one we'll talk about is a lead compensator. And this, in a lead compensator, the idea is that the magnitude of the zero, which in this case it has to be real because it's a single order polynomial in the numerator, but the magnitude here is smaller than that of the pole. And so that means that on the pole zero diagram down here, the zero is going to sit closer to the origin than the pole does. And so that means that you can think about this as being a softer version of PD control because remember the derivative in part of the PD controller is what added the zero to our PD controller. And so in the same way, the dominant force here is the out of this pole and this zero is really the thing that's the closest to the origin. So this is most similar to a derivative controller, and we'll see on the next slide that if we take this pole and take it very, very far out on this real axis and make it very close to minus infinity, then this effectively works as a PD controller. And so depending on where you place this pole, you can make it closer to PD control or closer to something that exhibits what this lead compensator brings to the table. So this controller obviously has three different pieces. It has the placement of the zero, the placement of the pole, and then of course the gain k. And so we get to pick all three of those. And so we'll see some techniques along the lines of loop shaping to help us understand how to do that. That uses frequency domain tools, but we also use a lot of trial and error and then also some experience. So like a PD controller, the lead compensator acts like a PD controller, and so that means that it provides a positive phase to the overall transfer function. And so again, that kind of comes from this idea that the phase of a zero is positive. It goes from 0 up to plus 90, and this lead compensator is really dominated by this zero, and so it follows suit in a similar way. If we wanted to show that precisely, we could evaluate the lead compensator at I omega and separate it into its real and its imaginary parts and observe what the angle or the phase is, and we'd see that everything is positive except for this quantity here. Everything's obviously positive because it's quadratic, and so on. But this p minus z, if the magnitude of p is larger, then this value here is positive, which makes overall phase positive. We'll contrast this with the other option, which is called the lag compensator, where the roles of the magnitudes are reversed. So the magnitude of the zero is larger than the pole. So when we think about the lead compensator, we kind of think about it in terms of a PD controller and a softer version of PD control. And so what does that mean? If we look at the PD controller, we have a gain and we have this zero, Z. And so the Bode diagram that represents the frequency response of this particular, just this transfer function, looks like these two plots here, where the magnitude essentially is very close to zero and bends at the value s is equal to I omega, where omega is z, and then it bends up at 20 dB per decade, and it increases. So that means that the magnitude is growing after the frequency z. The phase is an increasing phase, so it goes from 0 and it breaks again at omega is equal to z, and then goes up to plus 90. And so the value of the PD controller is that it can actually add phase at frequencies in this region. So in this region, it's adding a significant amount of phase, which allows you to improve things like the phase margin, which has impacts on stability. And there's also consequences on speed of response. The problem with this is that we get increasing amplitudes as frequencies get larger and larger. And one example of a very prevalent source of high frequency components is noise. And so this means that a PD controller is very susceptible to amplifying the noise which occurs at large frequencies. So one way of getting around that is to introduce this idea of this lead compensator, which essentially does the same thing. We can kind of think about this top part as doing the exact same thing that the PD controller does, but now we're going to add an element that corresponds to this pole. And so remember, the pole is farther out, so it means the pole is larger. So let's say the pole happens somewhere over here, and so the pole magnitude plot stays close to 0 and then breaks, and it breaks down at minus 20 dB per decade, going down. And so if you were to add the contribution from this plot, which come from the 0, and this plot, which came from the pole, you would get this overall plot, which essentially makes this vague S shape, so that it starts increasing at 20 dB per decade because of the effect of the 0 having already broken after omega is equal to z. And then this negative slope that is introduced by the pole essentially rectifies that and brings that back, and so now it tapers off to a finite value. And so depending on essentially how far away the 0 and the pole are, that introduces a range that allows the magnitude to grow. And one of the consequences of this is that this truncates the magnitude, and so these frequencies, after a certain point, essentially the amplification of these frequencies is truncated. So it only goes up to this finite value, whereas before this just kept increasing up and up. In the phase, a similar thing happens. So if our pole is located at a higher frequency because it's located further away from the origin, then that means that its phase plot looks something like this, where it stays close and then it breaks and goes down to minus 90. And so again, it's between Z and P that the interesting things happen. So we start to get growth of the phase in the positive direction because of the 0 and because it happens first as we move from 0 to positive, greater and greater values of omega. And then this dip in the pole, that downward trajectory, then subtracts away the positive part that the 0 added, leading us kind of back to where we started, near 0. And so the phase plot has this bump in it, and so this gives you the ability to provide a phase advance, so to improve essentially the phase margin, but only so much as within the range of Z to P. So we can't affect things after the pole over here or over here, but we can add phase to frequencies here, which may be enough to provide better stability of the system. So to compare with the lead compensator, we also have a lag compensator. And again, the idea here is that the roles are reversed. So it's the pole that is closer to the origin and the 0 is farther away. And in the same way that the lead compensator was similar to PD control. Now that the pole is the closest thing to the origin, this is most similar to a PI controller. And so this is, you can think about this again as a soft version of PI. If you went through the derivation of the phase, you'd observe that P minus Z, essentially it's the same transfer function, it's just the fact that Z and P have a different relationship. And so if you look in that arctangent, you'd find that that term would now be negative, which makes the overall phase negative. We still have to pick this K, Z, and P, and so as long as the zero is further out on the negative imaginary real axis, it is a lag compensator. Now continuing the comparison between PI controller and the lag compensator, we can look at the magnitude and phase plots of a PI controller and compare it with the lag compensator. So here we're comparing something that is very similar to what we've been looking at with PI control, and it just represents having kind of that proportional gain and the integral part. And so what ends up happening in the magnitude plot, the magnitude plot for 1 over s looks like a slope just directly downwards, like this. And the 0, as we saw before, looks close to 0, and then it breaks as it goes up. And so these two cancel out. This branch up here going up and this branch going down cancel out and provide us with this relatively flat region here. And then this relatively flat region and this slope here creates this slope that you see in the blue. And so that combination leads to this type of magnitude plot. In the phase, the 1 over s term contributes a minus 90 straight across all frequencies. And then the 0 adds a phase increase as omega increases. And so we get this blue curve here. What we notice about this is that this helps with steady state error. We already know that about a PI controller. And part of that is because it increases the magnitude at low frequencies, relatively low frequencies. One's lower than Z. One of the consequences of doing that, we get that benefit, but this decrease in the phase here can actually hurt stability depending on our system. And so this specifically is degrading the value of the phase margin, which has impacts on stability. So to try to make this a little bit better to work with, the lag compensator provides a softer version of this, where now we get a little less benefit from this increasing magnitude, and this is created by introducing a pole here, and that pole again is what is counteracting this upward slope that we saw over here on the PI controller, and flattening it out by the addition of the extra pole magnitude. And then the phase, again, instead of it being straight across the board, now the phase has a decrease due to the pole and then an increase due to the 0. And so now that the pole happens first, that phase decrease happens first. And so now we get a degradation of the phase margin within the range between P and Z. So in this case, it's really the magnitude that holds the benefit, and we're trying to mitigate the effect of the essentially negative impact of the negative phase due to the PI control, and we do that using a lag compensator. The final one that we'll introduce is the notch compensator, and this is simply an extension of those. So now we have 2 zeros and 2 poles in our compensator, and now this opens up the possibility that they're not just real values. So again, you could have a lead and a lag compensator put together as part of a overall compensator, or you could create a notch compensator where this specifically means that you have complex valued zeros and complex valued poles. And these can be, there's not really any order in this case, so these can be oriented however you want. And the Bode plots look in a very similar way, because essentially the phase looks very similar to as if you had 2 poles and 2 zeros. And then the magnitude looks very similar to actually what the lead and the lag compensator provide, depending on the orientation of these poles and zeros, which one's closer to the origin. Because remember, the overall plots of the magnitude and the phase. So if you have 1 over a quadratic, you have 2 poles, complex poles, then you're going to get a negative phase. And the breaking point of that phase is actually around, motivated around this omega n value. And the same thing, so with a pole, you would have a notch, and then it would go down. And so this notch, the placement of that notch, is again where that frequency value is. So changing that frequency value here or here shifts where they are. And again, that omega n, remember, that's this magnitude, essentially the distance from the origin out to either of those. And then the damping is what makes this notch particularly peaked, or this slope particularly steep. And so depending on how you select those, you can get different shapes, but they're kind of a perturbation on the same theme as a lead and a lag compensator.